All right, so in chapter 3 we start our study of systems of equations, systems of linear equations. And this is kind of nice because um, with these systems, we're dealing with something that usually is familiar with to people. You've probably taught them in your class, and certainly you've learned these things. So some of the things that we do today or in this lecture will be review, and that's okay. But what we want to do is we want to study the simple systems like the 2 by 2 systems and even the 3 by 3 systems, um, and identify properties and characteristics of those systems that carry over to larger systems and become important to us. So we'll mention those as we go along. Let's start just by reviewing the ways that we solve these small 2 by 2 systems. And so this system here is a 2 by 2, what I refer to as a 2 by 2 system, because it's got two equations and two unknowns, x's and y's. It's linear. Okay, that's important. We're going to focus mostly on linear stuff in here. It's linear because all of your variables are to the first power. All right. We don't have any x squareds or y squareds. So we like linear systems because they behave in predictable ways, and in fact, not only that, linear systems show up in a lot of different places for us, and we'll see some of those as we go along. Of course, what it means to solve a linear system means to find an xy pair that is a solution to both equations. Now, we know this, for instance, right, that this equation has an infinite number of solutions, an infinite number of xy pairs that solve it. This equation likewise. We're trying to find the one, or this more than one, we'll talk about that later, that solve both at the same time. All right, so just real quickly, let's go through the three methods of solving a linear 2 by 2 system. All right, the first method that we use is graphing. Now, this isn't a great method because our graphs have to be pretty accurate, but it is a good method for answering certain questions about the solutions themselves, the system's solutions. So if I want to graph it, I'm going to do just exactly what that says. I need to graph both of these equations, and to do that, that means I'm going to, have to put them in slope-intercept form, right? So we get our first equation becomes that, and our second equation is going to become 1/2 x minus 4. And so we need to graph those. Now, of course, we can graph them by hand. Let's do this a little more carefully since we do have some graph paper here. Graph these by hand. So our first equation, a y-intercept of 1/3 and a slope of 1, 2, 3, 4, 5, 1, 2, 3. Down 5 over 3. It's not quite there. There. And there's our line. Our second equation, when we graph it, y-intercept of -4 and a slope of up 1 over 2. And so there it is right there. And of course, the solution to the system will be the point of intersection, because when we graph an equation, right, all the points on this equation are solutions to that equation, or on that line are solutions to that equation. All the points on that line are solutions to that equation. So the solutions to the system, we need the pair, the numbers that solve both at the same time, and that's going to be our intersection point. So to solve by graphing, you graph the lines and you look for the intersection point. Now, the problem with solving by graphing is you have to be pretty accurate, and it looks to me like we did okay here. Our solution is 2, -3. And you could check that out by plugging that in, right? Now, of course, technology is going to do this better for us if we want to use technology. And so we can take advantage of that here. Let's just take a look at GeoGebra. And so if we graph these two equations in GeoGebra, y equals -5/3 2/3 x plus 1/3. That out of the way. And then our second equation. Of course, the nice thing, with GeoGebra, you can doll these things up. You can add color and whatnot. Y equals 1/2 x minus 4, I think. And there it is. And there's our color. And there's our two equations. And of course, from a graph, you can, if you're graphing it on graphing utility, you can pretty easily see the solution there. But with GeoGebra, you can actually tell it to give you the intersection of two lines, and there it is, a equals 2 minus 3, right? So with GeoGebra, we can create the graphs that we want, and let's just put that right here. See if we can resize it to a usable size. And we can see that we did all right with our graph, right? Okay, but that's graphing. So let's move on. The next method that we use to solve systems is by substitution. Right? Now, we don't often use substitution in this class. We will move on to the third method more often than not, but let's just remind ourselves how this works. You have your system, and you pick one of the variables from one of the equations. It doesn't matter which. Usually there's an easier one. In this case, it's going to be that x is probably the easiest. And so if we solve for it, that gives us x equals 2y plus 8. And that gets substituted into the other equation for x. So we have 5 times 2y plus 8 plus 3y equals 1. And what happens there, of course, you notice, is we get rid of all of the x's. Now we just have an equation in y's that we should be able to solve pretty easily. And it doesn't take us too long to get the solution to this as y equals -3. Now that's just the y part, right? We need an x part to that solution. So the easiest thing is to take that y value and plug it back in right there into that little thing that we substituted, or solved for. X equals 2 times -3 plus y, and x is going to equal 2. And so our solution is an ordered pair 2, -3. And so we want to make sure we identify that as an ordered pair. X will always be first. Okay, so we can solve by substitution. We don't often do that. Let's talk about our third method, elimination. Okay, and so if we take our system, right? The idea is this: when you're dealing with a system, there are two things you can do to the system that don't have an effect on the solutions to the system. The first thing you could do is you could take and multiply one or both of the equations by a constant. It can be a different constant. So for instance, I could multiply this top one. I don't know why I'd ever do it, but I could multiply this by 7. Right, I'm kind of abusing the notation here. We'll just multiply everything by 7 to give us 35x plus 21y equals 7. And that is going to, and then if I pair that with the other equation, I don't change the solutions. Okay, so if you multiply one equation by something, you get a new system. The solutions are the same. Now that's true if I multiply both equations by something. So I could multiply the top one by 7 and the bottom one by 10. Okay, so that's the first thing that happens that I'm allowed to do without changing the system. the solutions. The other thing I'm allowed to do is add the equations. So just looking here, if I just were to add these two equations, I'd get a third equation. And if I take and use this, replace one of my original equations with that, I get a new system, but it has the same solutions. Okay, so I can add equations together, and I can multiply one or both equations together without changing the solutions. So here's what I'm going to do. I'm going to creatively or carefully multiply and add and get a new system. Hopefully that new system is solvable. Alright, so probably you guys already know where I'm going to go with this, but here's what I'm going to do. I first look at this system and I decide, okay, what do I want to eliminate? Do I want to eliminate the x's or the y's? Let's say I want to eliminate the y's. To do that, I'm going to multiply this one by 2. And see what's going to happen when I multiply it by 2? It becomes a 10x plus 6y. Make sure you multiply everything by 2. It becomes that equation. Alright. Now, I'm going to multiply the second equation by 3. And when that happens, I get a 3x minus 6y equals 24. And so those are going to be that's going to be my new system, right? So I can change both equations, or I can just change one. In this case, I changed both. And this new system will have the same solutions as this system. All right. This system will have the same solutions as that system because all I did was multiply, scalar multiplication. Okay, but that's not enough. Remember the other thing I can do here. I can add equations without changing the solution. So I'm just going to take those two and add them straight away. And look what we get. Let's try that again. I get a 13x and then a 0y, which is just 0. Do not disappear on me. (13x) plus 0y, which is just 0, equals 26, right? And look at that equation. That equation has the same solution as the original ones. What is it? In this case, I can just immediately solve for the solution to get x equals 2. And once you know one of the two solutions, you can now just plug that into any of these equations to figure out what y is. All right, and I'll let you do that. Usually I'd probably pick that one. That's probably the easiest one to work with. But that is elimination. Elimination is the method we're going to use most often. So you want to multiply one or both equations by constants so that you can add them and have a variable eliminated.